12.6 is about tessellations, and I think you guys have heard or learned about this in previous years of working with math. A tessellation has translation symmetry. If it could be translated along a vector so that an image coincides with the pre-image. So if I were to draw a vector, you guys kind of sort of did vectors in another chapter. Remember, it looks like that. Magnitude and direction, remember we goofed around about this? If the image can be translated so that the pre-image and the image coincide with each other, then this is called translational symmetry. Okay, so the notes, go to the notes, go to the notes, go to the notes, go to the notes. Translation, all a slide all the way across, one image coincides with the next. A pattern with glide reflection symmetry coincides with this image after a glide reflection. So I want you to think of glide as in like sliding and then flipping over, sliding and flipping over. So like here, if I take this paw print and slide here and then reflect it over, slide here, reflect it over, slide here, reflect it over. So it's a glide reflection. Many symmetrical patterns are known as frieze patterns, and this is a pattern that has translational symmetry along a line. Both of the frieze patterns that are shown below have translational symmetry. The pattern on the right, though, if you take a look right here, has glide reflection symmetry as well, because this one moves over and then flips over, flips over, flips over, so on and so forth. This is just one right after the other. Okay, so identify the type of symmetry in each of these frieze patterns. This first one here, if you take a look, has this image. I'm going to try and, this is the pattern here. All right, so if I were to slide this over and then reflect it, would you end up with the same thing down here as you would up top? Not exactly. So it can't be a glide reflection. However, it does have translation, because if I take this and I move it here, it's the pattern again, and then I move it here, it's the pattern again there. So this is just going to be translation symmetry. All right, now if you take a look at this one, and I'm going to try and outline the pattern here. Well, it's kind of hard to do here. What's going to happen is you're going to take your pattern and then you're going to slide it over. However, if you slide this and then reflect it, you do get the part here down here. Do you see this? If I slide that there and then move it, it gets reflected down here. So since it does that, it is a translation, but it also has glide symmetry. So this is a translation, but it has glide symmetry as well. So working into our tessellations, a tessellation is considered like tiling. It's a repeat pattern that completely covers a plane with no gaps or overlaps. If you think about this, is like a tiled floor, right? What's very important in a tessellation is that the measures of the angles that meet at each vertex have to equal 360. The reason why? Because when they all meet, you end up with a circular figure that you kind of have there with something in the middle. All of those angles have to add to equal that 360. For that reason, only regular shapes can tessellate. Only regular shapes that can tessellate are the square, the triangle, and the hexagon. Okay? Regular shapes have to be the square, the triangle, and the hexagon. In the tessellation shown, each of the angle of the quadrilateral, occurs only once at the vertex. Because the angle measures of the quadrilateral add to 360, circle here, any quadrilateral can be used to tessellate the plane. 4 copies of the quadrilateral meet at each vertex. The reason why? All 4 angles are supposed to add to equal 360. So if I want to tessellate this figure, you're going to have to get each of those corners at each vertex in order to add to equal the 360. All right, the angle measures of a triangle add to equal 180, right? So this means any triangle can be used to tessellate, but 6 copies of the triangle have to meet at each vertex. Okay, so you're going to have 2 blues, 2 yellows, and 2 reds meeting at each vertex. In order to add to equal the 180, you have to double them to equal the 360. A regular tessellation is just simply formed by regular polygons, so like an equilateral triangle, so on and so forth. A semi-regular tessellation is formed by two or more regular polygons, with the same number of each polygon occurring in the same order at each vertex. So triangle, square, triangle, triangle, square, triangle, square, triangle, triangle, square, so on and so forth. They end up with the same pattern. Semi-regular, just think it's not going to be the exact same thing over and over again, okay? So, wonderful confusion. Let's go and try to figure this out. It says classify each tessellation as regular, semi-regular, or neither. So if you take a look here, the first instinct is to say regular because you have all of the same figure that you're tessellating. However, if you take a look at this image, we said that the only regular polygons that you can tessellate are a square, a triangle, or the hexagon. This does not fall underneath those categories, so this would be a neither. The next one's nice and easy because they have all equilateral triangles here, so this would just simply be regular. And then this next one has a little mixture. It's got the triangles, the square, and the hexagon. So these are all regular, but since it's not all the same figure, this is going to be a semi-regular. All right, so determine whether or not the given polygon can be used to tessellate. If so, start the tessellation. All right, so this is a regular triangle, so this is going to be a yes. And we can simply start, oh, I'm going to use a different color. We'll start drawing the tessellation just like this. So on and so forth. All right. The next one, we've got a pentagon here and an equilateral triangle. And I'm going to ask you, can you tessellate this? And I'm hoping that you're going to say no. The reason why is because even though this is a regular pentagon, remember only the square, the equilateral triangle, and the hexagon can be the regular polygons that you can tessellate. So now I want you to go ahead and pause, and then I want you to determine whether or not you can tessellate these, and then if so, draw the tessellation. All right, so this first one, by itself, it would have to be no, because you would start drawing your hexagon here, and what's going to happen is you wouldn't be able to fit another hexagon here. You need something like a square to block it off, or a triangle, right? So even though I want to say yes, because it could be part of a tessellation, you're going to have to say no, because you can't just tessellate the hexagon all by itself. The next one, can you just use the square? Well, let's see. If I put squares at the end here, what else am I going to need, you guys? You're going to need some triangles, okay? So this is going to have to be a no as well. Even though you can tessellate with these, you need another piece in order to complete your tessellation. I know this is a bit confusing with the whole glide translation, tessellations, regular polygons, all this other stuff. That's why we watch these, so that we could spend the time on the questions in class. Come ready with those tomorrow and have a great night. Almost done, you guys.